So now we're going to deal with vector applications, which is basically going to boil down to some word problems. And the trick of doing these application problems is all of them are going to be given to us in polar form or some magnitude and direction value. We're going to need to convert them to their component value. So what I've done for you below right here is I've taken and shown a vector with its magnitude and its direction, and I've shown you the horizontal and vertical components. Now there's a relationship between these components and the magnitude given to you. The sign is obviously equal to the opposite, and I call this the vector's y component over the vector's magnitude, and I should probably put that in there. And if you multiply the magnitude by the sine of the angle, you get the vertical component. Likewise, if I take the cosine of this angle, that's equal to the x component over the magnitude of the vector. And thus, if we multiply the magnitude of the vector to the other side, I get the magnitude times the cosine of the angle is equal to the horizontal component. So what I want to now do is find the x and y components of vector A, given that vector A is 6 and 121 degrees. Let's sketch that out real quick. If this is my xy axis, and I go out 6 and up 121 degrees, I'm somewhere, let's call it here. So that's this vector. So I should get some x and y component where I have a negative x and a positive y. So I'm going to use this notation right here and say, all right, well, if I take the vector's magnitude of 6 and multiply by the cosine of 121 degrees, I should get my x component. And then taking 6 and multiplying by the sine of 121 degrees, I should get my y component. So 6 times the cosine of 121 is about negative 3.09. And then 6 times sine of 121 is about 5.14. So this is my horizontal component. This is my vertical component for the vector given with its magnitude and direction. Let's move on to some applications now. Our first example says that we have two forces with magnitudes given as 10 and 20, and they act on a singular point. And they want us to know what's the resultant force acting on that point. So basically all they're asking us to do is calculate the resultant, or the sum of force 1 plus force 2. So basically we're doing force 1 plus force 2. And these are both vector quantities. But the problem is we're given these two vectors in these forms that we can't really work with. Okay, the only way we know how to work with adding of two vectors is taking things in their component form and then adding the x components together and y components together. So I'm going to take and convert these. First of all, force 1 is given to us by 10 and 45 degrees. And force 2 is given to us by 20 and 150 degrees. We're going to add these two vectors up. Now if you think about this, if I were to add these two by tip-to-tail method, I start here, go up to the tip, calculate tip-to-tail, and connect. So this right here, I'll put R, is my resultant. So the answer we should be getting is some vector that's probably a little bit longer than either 1 or 2. And I could also, if I wanted to, calculate its direction, but this problem didn't ask us to, so we won't. All right, so let's go ahead and do these calculations. So we said in our first slide that if I wanted to find the x and y component of each of these vectors, we take the magnitude, multiply it by the cosine of the given angle, and the magnitude multiplied by the sine of the given angle. And that will be force 1. Force 2 would have the same calculation, magnitude times the cosine of the angle times the magnitude times the sine of the angle. And then we simply do those calculations. So after doing these calculations, we see that we have an x component of 7.07 and the y component is also 7.07. And then we have an x component over here of negative 17.32 and a y component of 10. So in order to add the two forces, I add the x components together. Adding these x components together, I get negative 17.32 added to 7.07. That's going to give me about negative 10.25. And then adding 10 to 7.07, I get 17.07. And this represents the sum of the two forces. Now, if I want the resultant force, they didn't ask for the component form of that. They asked for the magnitude of that. So the resultant force is equal to the magnitude of this. So I have to take 10.25, square it, and that's a negative. Add that to 17.07, square that, and square root it. And that's going to get me roughly 19.91 pounds, since that's what we're working in. Let's move to our next example. All right, so in this example, we've got some woman launching a boat from one shore across the Straight River, so drawing a picture is probably a good idea, and wants to land directly opposite. So she wants to be, she's starting here, she wants to end right here. If the speed of the boat is about 10 miles an hour and the river is flowing directly east at a rate of 5 miles an hour, so the river is flowing this way, all right, we want to know what direction she's got to head in order to arrive over here. All right, now, if I set up vectors to represent all of these speeds, then here's what I should have. The river is moving at 5 miles an hour. She wants to end up straight across. So she wants to end up straight over here. This is actually her resultant. Okay. And then the boat is going to move, have to move, at this direction. If you've ever rowed a rowboat or any kind of boat in a current, you know the current pushes you back the other way. It's like swimming in the ocean. The riptide takes you down the shore, and then you got to walk back. So if you look at this, and I were to do a tip-to-tail calculation, and you'll see that adding the boat movement to the river movement gets me my resultant, which is straight across. So think about what I'd have to do here. I'd have to take, I'm going to call these three things as follows. I'm going to call this the river, the boat, and I'll call it my resultant. And if I take my river, we'll go R, R's is call the resultant a capital R. All right. I have to take my Rx and my Ry here, add that to my Bx and my By here, and when I'm done with that, I get my resultant X and my resultant Y. So that's what I'm going to want to do. Now, you'll notice that in the end of this problem, they're asking, what direction do I need to move at? All right. Well, direction implies, ooh, I need an angle. I need some theta value. Or I could use this theta value here. It doesn't really matter. So when I'm done, I'm going to be given an x and a y, and I'm going to have to calculate an angle, which means that if I'm given some x and y value, and I have to calculate this angle, I'm going to have to use a sine or cosine in the end to get my answer. All right, now you'll notice that in this case, my river, I can get my x and my y components pretty easy. You'll notice that in this, I have a x component of 5 and a y component of 0, as you can see in the picture. To find whatever the boat x and y components are, I'd have to actually use the magnitude, which I do know, 10 times cosine of some theta, which I don't know, and 10 times some sine of some theta, which I don't know. That's going to give me my resultant vector. Now, I do know something about my resultant vector. I know my resultant vector is going to have an x component of 0. And I know that its y component is going to be whatever 10 sine theta is, but I don't know what value that is. So if I look at what I have in my problem and I want to find my angle, notice I know that 5 plus 10 cosine theta is going to equal 0. Well, I can solve for theta in this, and since theta is what I'm trying to get as an answer, because I'm looking for what direction should they head the boat in, I can go ahead and do some simple algebra. So I have basically what, negative 1/2 is equal to cosine of theta. Right? And if I take the inverse cosine of that, then all I have to do, pop that in my calculator, and I end up with theta equaling 120 degrees. So instead of this angle right here relative to the west, they've given me the angle relative to standard position, which is fine. All right. So I'd have to head at 120 degrees of east in order to get straight across the river, which makes sense. All right. Let's do another example. So in this problem, we've got a situation where two tugboats are pulling this big ship, and we want to pull the ship in a straight line. And they want to know, what do they want to know? They want to know if the ship is going to travel on that straight line, what angle does that top ship have to be at? All right, well, this is a similar problem. The vectors are drawn here for us. So what we want is we want to basically take, we'll call this, how do I want to do this? Let's call this tug 1 and tug 2. All right, and we'll call this the ship. All right, so I'm going to have to take tug 1, add that to tug 2, and that equals the ship. All right, and if I were to set this up, I know that in this case, tug 1 is going to, which one's the larger tug? That's the larger one. All right, so that's going to be given as a vector with x and y coordinates. And the second tug is going to have x and y coordinates, or vertical and horizontal components. And that's going to equal the ship and its x and y components. Now, what do I know about each of these? Well, as we've done before, when we've converted from polar to rectangular, we've taken our magnitudes, which in the first tug's situation is 4,000, multiplied by the cosine of some angle, which I don't know in this case for the first tug. And I'm going to add that to 4,000 times the sine of that angle, which I don't know. And in tug 2's case, which has an x component of 3,200, cosine, well, in this case, I have an angle. And it shows 30 degrees, but it's 30 degrees in the negative direction. So I'm going to say negative 30. And 3,200 times the sine of negative 30. Whoops. And that's going to equal the x and y components of the big ship. Now, the x and y components of the big ship, I know one of them. I know its y component is going to be 0, which makes life convenient. All right, I don't know the other component. All right, and they asked if the ship's going to travel on a straight line, what angle does the larger tug have to make? So again, this is just like the problem I previously did. I can find out this angle by setting the sum of these two, 4,000 sine theta plus 3,200 sine negative 30, set that equal to 0. Right? Well, if I take 3,200 and multiply that by sine of negative 30, I end up with roughly negative 1,600, which is what I should have because it's in the fourth quadrant. Bring that over to the other side, and I get 1,600 divided by 4,000, which is roughly 2/5. And that's going to equal sine of theta. Take my inverse sine of 2/5, and that's going to get me about 23 degrees. And actually 23.6 if we were going to go into decimals. And that's the answer that I gave you in the initial problem. So there we have it. So the trick to all these is finding out the x and y components, adding them up, and getting some kind of z component. Setup on this last problem is a little bit tougher. All right. Now it says we've got a sign hanging from two supports, and we want to know what are the magnitudes of the forces exerted on the sign by each support bar. All right. So the deal is these two forces have to add to the force of the sign hanging down. And they don't really tell you that, but that's typically the case of the problem. All right. So in order to get this problem done, what we're going to have to do is add the two vectors, F1 and F2, and that's going to equal the force on the sign. All right. Now, in order to represent that accurately, okay, the force on the sign's hanging directly down. So that sign force of 100 is going to have to equal sum of two other forces. And if we were to do this in a tip-to-tail method, if you will, all right, one force would have to be going to the right, and another force would have to be going down in this direction to get a resultant force of this type. Okay, or another way we could represent this is we could say, in order to get my magnitude of 100 going straight down, I'd have to have force going to the left and a force going down this way, going tip to tail. Now, if I look at my drawing, I think the best representation of that is probably this one right here, where this is force 1 and this is force 2. All right. And what I've really done is I've copied that from this picture here. I've slid force 2 down this way. All right. So here's what we're going to do. We're going to calculate the x and y components of each of these. All right. If you look at force 1, all right, force 1 is going to be given by its x and y components. Now you can see that it's on a straight horizontal. All right. So if it's on a straight horizontal, it has no vertical component for its force. The horizontal component is just whatever the force exerted on it is. Force 2 is at an angle. So we know that force 2 can be given by F2 cosine of whatever its angle is. Now we have the 60-degree angle hanging right here. And I know that 60-degree angle is represented by this angle here. So since I have two parallel lines, if you will, in this picture, all right, then I have an alternate interior angle, thus meaning that I can say this is 60 degrees in this case, but it's going to be negative since it's hanging down. Notice how I copied that in this picture. And then this is force 2 sine of negative 60. Now the sine has no x component since it's hanging straight down. So that's going to be 0. and then it does have a y component of 100. So if I look at this, I can calculate force 2 by taking 0 plus force 2 sine of negative 60 and setting that equal to 100. Sine of negative 60 is roughly negative 0.866. And if I divide 100 by that, then my force 2 is going to be equal to about negative 115.47. If I take its actual force or its magnitude, this negative actually just shows me its direction. Okay, then it's about 115 degrees or 115 pounds of force. If I want force 1, I know I have another equation here that says force 1 plus force 2 times the cosine of negative 60 is equal to 0. But I've just found force 2. So I have force 1 plus negative 115.47 times the cosine of negative 60 is equal to 0. Find out what negative 115.47 cosine of negative 60 equals, and we've got the problem solved. So I know that force 1 plus this quantity ends up being negative 57.75. That's equal to 0, so force 1 is equal to roughly 57.75 pounds. And thus the problem is solved. All right. Give these two problems a shot, and we shall go from there.